Okay, dear colleagues, let us start our last seminar in this year, last BIMS Integrable System Seminar. And today our speaker is Xin Zhang from Institute of Physics, Chinese Academy of Science about chiral coordinate Bethe ansatz for XYZ and XY and XX spin chains.
Okay, first I want to thank the organizer of this seminar. So I'm Xin Zhang from the Institute of Physics, Chinese Academy of Science. So today I will give a talk about our recent research, the chiral coordinate Bethe ansatz for the anisotropic spin chain. So the talk today is based on this. So the result in these three papers, and there's my collaborators, Andreas Klumper, Frank Gorman from the Germany, so the University of Wuppertal, and Slava Popkov also in this university, and also the University of Ljubljana. So in past few years we did a lot of job for hello. So in past few years we did a lot of job for this anisotropic spin chain. So this is the outline of my talk. So the first part is a very short introduction about the anisotropic spin chain, and on the second part, I will introduce the chiral coordinate Bethe ansatz for the spin half XYZ model. And in the third and the fourth part, I want to make a introduction about our chiral coordinate Bethe ansatz for the XY model and also for the XS model. So the first part, the introduction. Let's first start from the XYZ chain. So the XYZ chain is the most general isotropic spin chain. So it's a very famous integral model. So let's see the Hamiltonian. So in this Hamiltonian, Hamiltonian just describe a neighboring site spin interaction in. So how to say? So here in this talk, we just start the periodic system. So with this periodic boundary condition. So here, so for the XYZ chain, so the exchange coefficient in 3 dimensions in the X chain, in the X direction, in the X direction, Y direction, Z direction, they are different. So here we just use this theta function to parameterize the exchange coefficient. So in this parameterization, we have a crossing parameter eta and also a complex number tau. So here is we just use this notation. So for this, so here this theta k is just the standard theta function. So here in this one, we know theta function has 2 periods, right? So here, so one is tau and another is tau. So it means, so in this exchange coefficient, we have 2 free parameters. One is eta and another is the period of this theta function tau. So we only focus on this emission system. So in and which conditions, so the system is emission is, so when this tau is purely imaginary and eta is real or purely imaginary, and we can get emission Hamiltonian. So the spin half XYZ chain is the very typical quantum integral model without U1 symmetry, and has many applications, and in the statistical mechanics and condensed matter physics. So here is some famous method about this model. So the first one is the boxed famous job about the 8-vertex model, about the construct the R matrix of this model and proposed the famous TQ relation. So then the Takhtaji and Fadiev, they just use another language to recover the boxed solution, what we call the algebraic Bethe ansatz. So the third one is the eigenvalue problem of the XYZ chain with various integrable boundary conditions was solved by the off-diagonal Bethe ansatz. So in this in the off-diagonal Bethe ansatz, we do not need the we do not need the reference states, and we do not need to construct the Bethe state. We just diagonalizations. We just diagonalize the transfer matrix directly without using any reference states. So in this talk, in our work, we just studied the periodic XYZ chain, but this eta we let eta take in the root of unity. So what is the root of unity? So here we consider a system with the system lattice size, total lattice size is n. So m is an integer, and the tau and the 1, they are two period of the theta function. So here is what we call this root of unity conditions. So this first and the second equation, if they are satisfied, what we call the root of unity condition. So here is f is the smallest non-negative integer to satisfy these equations. So we see that if the capital M is not n over 2, in fact this s plus 1 has a limit. So how to say it cannot be larger than this the absolute value of n minus 2m. But there exists a very special case is when the n is even and the system and this number this integer m is n over 2. So the first equation is satisfied automatically, and for any eta. So then this s here, this integer here can be arbitrary non-negative integer. So from our results, we realized so this third case is different from the other two. So the reason, so why we study this root of unity condition, because at a root of unity condition, we can find an expression for the eigenstates. So the eigenstates just contains finite terms. So we can easily prove that so the base states or is convergence. So but if this is not a root of unity, so the eigenstates always contain infinite terms. So his convergence condition has not been proved as far as what I know. So then there is the main part of the first part of our main work about the periodic XYZ chain at root of unity condition. First, I want to introduce a local vector, so which was first introduced by Bakst almost 50 years ago. So then this is so how to say this local vector are also parameterized by the theta function, but this fits. But now for this theta tilde function, so it also has two periods. Causal period. So one is 1 and the other is 2 tau. So it's different with the theta function in the exchange coefficient. So then one can construct such a factorized global vector. So here U0 is just a free parameter, and we can see that if we see this so the argument u in this phi u as a phase factor, so we can say that just in this global vector we have two different components. First is we call this d, and then is this n1 and nm. So I will introduce the meaning of these two different factors later. So I want to say, just if we see this, if we treat this u in this phi u as a phase factor, we see in this global vector, so that this phase in the global vector just increase linearly. For example, from the site m to site m plus 1, this factor increase an amount eta. But there's some different case is what happened in this point n1 and nm. So we can say, for example, from this nk to site nk plus 1, so that this phase does not increase an amount eta, but decrease an amount fixed amount eta. This is what we call kink. So in our 2 years work, we find this, so how to say, the local Hamiltonian and the local vector in the local vector satisfies such simple factors. We see that on the left hand side is this is the column vector, right? This is 4 times 4 matrix, and this tensor product with this phi and this phi on the different sides. So this is the vector with 4 components, right? So in general case, on the right hand side, we also need 4 terms. But here we see that, so if the component, if the phase factor so the difference is eta or minus eta, on the right hand side, we only need 3 terms. So the other terms in the generic case just disappear. We can find this such a simple identities, and then also this use this sigma n and this sigma zeta act on this phi is a linear combination of this phi and also this phi plus or minus 2 eta. So then, just based on this fundamental identities, we can prove that. So and the root of unity conditions. So we let the Hamiltonian acting on these vectors. We see that so the Hamiltonian acting on these vectors is also a linear combination of this eigenterm, and the other term is so one of the position of the kink with the shift +1 or -1. So here we just know that, so if this so how to say, if this ng and ng +1 are 0 are equal, and this eigenstate is just 0, it's a trivial. So then the periodicity of the theta function implies that. So we can say on the right hand side we will have this the kink of the position of the kink has a shift +or -1. So if this index is larger than n plus 1, and so if this n is larger than n, like n plus 1, and then this state is proportional to the state with the shift for this first d, for this d factor. So if this component, so if this one is 0, and then we will this state is just equivalent to the state with the shift for this, with the shift -1 for the first index d. And then just from the periodicity of theta function, so if d, so the state with the d and d plus s plus 1, they are equivalent. So then we can easily prove that just from this identities, we can prove that. So, and the root of unity conditions, so this vector, so this n is so -1, so 1 less than n1 less than n2 and to n, and this d just takes this takes some discrete values from 0 to +1. So using these identities, we can prove that, so these vectors can form an invariant subspace. So it means, so the Hamiltonian acting on this arbitrary, on each vector is a linear combination of this set of vectors. So how many vectors in in this set, the total number of the vectors in this set, what we call this D M of S, is the S plus 1 times binomial parameter. So select M from the N. So this is the figures for the states. So for the x-axis is the system size. So here, because the states, they are all factorized, so we use a set of the factors we call ydn to parameterize this vector. So we see that. So we can see that. So this phase factor increase linearly, but at some point there will be a shift. So what we call kink. What we call kink. So so the number of the kink is just the capital M. So the integer M appears in the root of unity condition. So what's the meaning of this D? So this is meaning of the D. So if we see these figures, we see that this N1 to Nm just the determinant the position of the kink, but this D determinant the phase on the first side, right? So for example, if this D has a shift, D plus 1, we will get another branch. So it means in this one, we have this S plus 1 branch. So different, just depending on the starting point of the phase on the first side. And then this N just determinant the position of the kink. So there's a remark. So if M is not N over 2, we checked numerically that the dimension of the invariant space is just equal to the number of the vectors in the basis. So another thing is if we change the sign of the chirality eta to minus eta, so we get so the Hamiltonian is the same. So we get another set of linear independent basis vector with the same dimension. So the vector with positive or negative chiralities are all linear independent, so that there are two invariant subspace with different chiralities and with the same dimension. So that is the another remark is why we call chiral coordinate, because the phase, we see this phase increase linearly. So it's like a chirality. So since this reason, we just call our beta ansatz, this is a chiral coordinate beta ansatz. So after our work, we just realized that 50 years ago, Baxter has introduced some similar basis. So here is I want to make an introduction about the Baxter spaces. So in Baxter spaces, so how to say, he also used this phi function. So the local function is the same. So the local vector is the same. But in Baxter spaces, so here, for example, in Baxter spaces, he introduced more free parameters. So here, there's for example, there are two free parameters. Y is R0 because for the I want to say for the red part, it's just like the spin up, and for the blue part, it's just like a spin down. In the case with U1 symmetry. So in Baxter spaces, we see that there's chiral states. So the phase increase linearly, but at this number of the kink, it's just you get another parameter t, and then is also the we can say this spin up and then spin down. So this is spin down, spin up. So so I want to say in Baxter spaces, his basis is more like the spin. This is some. So there's some so-called this quasi spin flip based on this all spin up or all spin down state. So in Baxter's work, he also proved that under the root of unity, such a root of unity condition, So this boxed spaces, so this set of the states also form the closed closed subspace for the transfer matrix of the XYZ chain. So what is the difference with our basis and the boxed spaces? So there's some remark. So if we use a set of the parameter to represent the vector, the basis vector, first we know that, for example, in our basis, if the d, if we change this d to d plus 1, so this phase factor y has a shift of 2. But in boxed spaces, maybe this is a typo, right? So if this d is replace d with d plus 1, so boxed spaces, so the phase factor just has a shift 1. So that is the difference. Another difference is that in our vectors, the d can take s plus 1 values, but in boxed spaces, the d can take values q. Q can be s plus 1 or 2 times s plus 1. So that is the difference. So the basis is we can say is different, because just if we replace d with d plus 1, so the shift for the phase factor is different. Another one is in boxed spaces, there's 2 free parameter, these R0 and T0. But in our basis, there's only 1 free parameter U0. So it means, so our chiral vectors has a simpler structure. The third and also the most important thing is that, so what's the main difference between our approach and the Box's approach? Because in Box's approach, he just used the transfer matrix. But in our approach, we just use the Hamiltonian. This is the difference. So our approach is independent of the transfer matrix, so which is different with the Box's one. So then I found Box's only study the periodic XYZ chain with its basis, but in fact for Earth, we use our basis to study the periodic chain and also the open chain. So then it's about how to construct the eigenstates of the Hamiltonian based on our basis. The first is the simple one. So when m is 0 case, so it means so this crossing parameter eta times the system length n is just a linear combination of these 2 tau and 2. So then we introduce such a state. So we can say this in this case, so the phase factor just increase linearly, right? So then we can prove that, so this state, this such of the capital phi of u plus or minus of u is chiral, and this sign just indicates the different chirality, and we can prove that. So this is an elliptic analog of the spin helix state in the XSZ chain. So when this condition is satisfied, we can prove that this phi 0 plus or minus of u is an eigenstate of the Hamiltonian. So here u is arbitrary. So just use this, so how to say, we can prove it in a very simple way. Just use the first equation. So all the unwanted terms are cancelled automatically and this condition. So then we can only get the eigenvalue term. So then we can prove that so such a factorized state is an eigenstate of the Hamiltonian and these conditions, and then so how to say, with arbitrary u, right? With arbitrary u, and then the energy is independent of this u. So the energy is just a constant, is independent on this the free parameter in the in the states, and then we can also get that so the energy level E0 is degenerate, and the degeneracy is at least 2 times n. So then is the beta ansatz for the states, for the eigenstates of the Hamiltonian. So this is the I have said that so this our state from an invariant space. So in principle, so all the eigenstates belonging to this subspace can be expanded as a linear combination of our bases. So then this is our basis, and then this is the expansion coefficient. So here we just use a set of the base roots, what we call base roots. This base roots has m components. So this expansion coefficient is this f, and then we need to know this sum for d from 0 to s. So then the energy, so the corresponding energy can be parameterized by the base roots in this way. So what is the ansatz for this? So what is the ansatz for the expansion coefficients? So we can use so how to say this? This is an ansatz for this expansion coefficient. So this function can be given by such a u function, and the u function. So this u function depends on this base root, and also there's a coupling between the base root and also the phase factor in the basis. So that is the difference with the case with U1 symmetry, like the XS chain or the XSZ chain or the XX chain, because in the U1 symmetry case we do not have this coupling, but in XYZ chain we have this coupling. And here, so this X is just a permutation of 1 from M. So if we see this this formula, this is quite similar to the it's just a coordinated beta ansatz, but it's the generalized one. So then the coefficient, the C, the coefficient or the amplitudes in the f function, in this f function, we have this also. So here we are sure that this is depends on this u, depends on this lambda on and also the phase factor um in the vectors, right? And then this coefficient C is also determined by the base roots, and they just determined by the two-body scattering matrix. So if we just change the position of this x n plus 1 and xn, we will get this two-body scattering matrix, and all the multi-body scattering matrix can be factorized by a product of the two-body scattering matrix. And then to ensure that so our ansatz, so our base state is an eigenstate of the Hamiltonian, so the base root should satisfy, and also this parameter W, this parameter W is just appeared in this alpha D, and let's go back. So we also has this factor alpha D, this alpha D here. So then this the base roots. So this M base root and another parameter W, they should satisfy such a following should satisfy this beta ansatz equation. So the first one gives us M equation, and the second one gives us another equation. So then, so how to say, so the our beta ansatz can give the eigenvalues and also the eigenstates, right? So there's some remarks. So the first one is just because of the periodicity of the theta function. So if this base root has a shift of 1 or tau, they are equivalent solutions. So it means they give the same energy. So and also the eigenstates are equivalent. So then we can let all the base roots lie with a basic cell of the theta function. Another one is that so the Hamiltonian is an even function of eta. So then there also exists another set of the beta ansatz solution with, so how to say, if we change eta to minus eta, w to minus w, but lambda is still the same. They give the same, they will give us another beta state. So these states corresponding to the same set of the energy, but different eigenstates. So then it means, so if M is not n over 2, so all the energies belonging to the invariant manifold are degenerate. So the third one is a third remark is about so how to say, the selection of this M. So in some cases we will say so the selection of the M may be not unique. There may exist a set of the integers M1 to MR satisfy the root of unity, and in this case we can find this R chiral invariant subspace. So for each of them, our procedure still works. An example is the XY or XS model with an even n, which I will introduce later. So in the beginning, I have shown that so this when this M is n over 2, the situation is different. So what is the difference? So this is the beta equation for the for this model, and here, so the number of the beta roots is just, so here is the first, the system size n is even, right? And then the number of the beta roots is n over 2. We get okay. So then this is the beta equation, but we found that apart from this basic equation, so the physical solution for the base roots, for the physical base roots, they satisfy another selection rule. This means so the sum of the base roots times 2 is k plus L tau 1. So here k and L, they are all integers. So then it's the question. So our basis is not complete in this case. We find numerically. For example, if the system size is from 4 to 12, we find the total number of the missing eigenstate. So what is the missing eigenstate? It means this eigenstate cannot be expanded by our state, by our basis. Is we can get such of the number of the missing states. But we know that in 2002, Baxter has discussed that. So the beta ansatz, so how to say, the beta ansatz equation in this case is complete. So then I want to say, so Baxter said, so the beta ansatz equation is complete, but in our basis, we find that, so for some states, we cannot construct the eigenstate with our basis vector. So there is a question. So if the beta ansatz equations, so the beta ansatz solutions are complete, so where are the eigenstates and the respective eigenvalues missing in our chiral subspace come from? And then from some numerical data, we found that, so in Baxter's work, he just proposed a very special solution for the basic equation, what Baxter called the bound pair. It means, so for one base root is in this position, eta over 2, and the other is minus eta over 2. And so how to say, so this factor goes to infinity. So for one base state, so this function goes to infinity. This factor goes to 0, but their product is -1. And then such a bound pair solutions contribute a constant to the energy. So then, if we just so how to say eliminate these two bound pair from the total base roots, and then the remaining regular base roots, this just satisfied such a modified beta ansatz equation. And for how to say for n is 4, 6, or 8, we check numerically that so the missing eigenstate always corresponding to the bound pair solutions. So there is a conjecture based on some numerical data. So the beta ansatz equations has two types of the solutions. So the regular one, which means so the this is also the majority one, right? And the one with the bound pair. So here we want to make sure that there's only one bound pair. So these two roots. So there's another name for this kind of the solution. They call this a singular solution, not the regular solution. So all eigenstates, this conjecture is that so all eigenstates corresponding to the regular beta ansatz solutions can be understood in terms of our simple chiral basis with kinks, and the bound pair eigenstate can be constructed using other bases like the box basis. We check numerically, but in this stage we don't know how to prove. And then is the discussion about so what happened for the XSZ model. So since we if we start from the XYZ chain, we can get the partially anisotropic XSZ chain by letting this so one of the period of the elliptic function go to infinity, and then we will get the XSZ chain. So, but we know that we just consider this root of unity condition. So here the parameter eta now can take some discrete real values because this tau goes to infinity. So here is eta is just a real. So it means so in this for the XSZ chain, so this root of unity conditions only exist in this critical phase. So when the absolute value of the delta is less than 1. So this is we also in XSZ chain we also has such a root of unity conditions. So then these equations are constrained and which chiral invariant subspace also exist in the in a periodic XSZ chain. But for the XSZ chain, the local vectors for the XYZ chain, so the local vectors is parameterized by the theta function, But for the XSZ model, so the local vector is just parameterized by the exponential function, right? So then the beta equation, so the beta equation obtained from the chiral coordinated beta ansatz are deformed one. So it means, so compared with the conventional one, there's some twist factor, like there's some prefactor, and this factor satisfies. So how to say this W, this e to the power of W satisfies such conditions. So it means, so at the root of unity, we can also construct a set of the chiral beta ansatz, and then the beta ansatz equation is just a deformed one. So another thing is about this phantom base root. So it's proposed by us. So when we call this phantom base roots, it means so the real part goes to infinity, and then this root does not contribute to the energy. So we see that in the if we let tau goes to infinity, and then we can find this base root for the XSZ chain and for the XYZ chain, they has such a one-to-one correspondence. So in this tau goes to infinity limit I times lambda g is the lambda g bar. This lambda g bar is the base root in the for the XSZ chain. So we see that in some case we find that if tau is large, but if tau is large, so the imaginary part of this lambda g will also be large. So this imaginary part of lambda g will increase with tau. But in this tau goes to infinity, this they will tends towards non-zero constant in this limit, and then the base root lambda g bar for the XSZ chain, they will be a phantom one. They will go to infinity, and then they will not contribute to the energy. So this will lead to the extra degeneracy in the spectrum of the XSZ chain. So how to say, compared with the XYZ chain, so the XSZ chain has a larger for some states, for some eigenspectrum. So how to say, it has extra degeneracy. So then we can see that, so the base roots for the XSZ chain, so in this case, they will be divided into two parts. So the first is the regular one, and the other is the infinite one. And for this infinite one, the real part will go to infinity. All the infinite roots, all the phantom one, the real part will go to infinity or minus infinity, and they form a string. They form a string, but the real part goes to infinity. And for the regular one, so how to say, after our numerical check, we found that the contribution of these phantom roots, they will give another prefactor to the base root, to the basic equation, and then we checked numerically that so the contribution about this phantom one, they will eliminate this twist factor e to the power of w in this case. So it means for the regular base root, so the basic equation is just the conventional one. So then is the one of our recent work about this XY model. We find very interesting, because here for XY chain we found that, so for the XY model we can we can construct a complete and also the orthogonal basis for the XY model. And then we proposed chiral beta ansatz for the eigenstates and calculate some interesting properties like the correlations, 1 point or the 2 point correlations. So what's the time? Okay. So then, so how to say, so how we get the XY model from the XYZ model? We can just let this eta to 1/2. And then the zeta component will be 0, and then the XY chain will reduce to the XYZ chain will reduce to the XY chain as so how to say in this form. So then this GX GY is, so how to say, GX is theta 3 over theta 4, and GY is theta 4 over theta 3. So the GX times GY is 1. So then so how to say, if we consider a periodic XY chain with an even number of sides, so we can say in this case we can let the number of the base roots, so the number of the base roots has the same parity with n over 2, and here so the s is 1. So when it is 1/2, we see that GX over GY is larger than 0. If we select it is minus 1/2 minus tau, so the XYZ chain will reduce to another XY model with so how to say, in that case GX and GY has the different sign. So because we have shown the details for the XYZ chain, so we can directly obtain the basis states of the XY chain from the result of the XYZ chain. So here we find very interesting, because so in the XYZ chain we have a free phase factor U0. So if we let U0 is tau over 2 and eliminate some overall factor, we can arrived a very simple set of the basis sector. So here is also a, so how to say, it's a set of the it's a factorized eigenstates. This is a state, and here we said that, so this kappa is so here this n is also the number of kinks. So here kappa can take values +1 or -1. So this kappa just related to the polarization of the first qubit. So when this kappa is 0, is +1 or -1 corresponding to the eigenstate of the sigma 1x with eigenvalues +1 or -1. And just to show this spaces, it means in this spaces all the qubits, or even all the qubits are polarized in the positive or the negative x direction, and all the even qubits are polarized in the a positive or negative y direction. And we can easily prove that, so these vectors are orthogonal. They are orthogonal and complete. And they form a complete basis for this Hilbert space. And they are all eigenstates of this winding number, winding operator V. This winding operator V is commute with the Hamiltonian of XY model. And all the bases are the eigenstates. All the basis factor are the eigenstate of this winding operator V. So this is the plot for that. So this on the left panel, this is just a very there's a famous one about this what we call SZ basis. So the first one is the reference state. So all the spin is on the spin down. This is spin down. So the second one is the one spin flip state. So on this side, so this spin is flip from spin down to spin up. And then the third one, this is the all spin up state, or we can say this is the all spin up state, or how to say it? So we can also say this is the, so in which state there is a maximum, right? So on the right panel, this is our state. So the first one is what we call this one, and this empty side is, so how to say, the first side, this qubit is on the x direction, and then it's the y direction minus x direction minus y direction is just like the anti-clockwise, right? So on the second one, we see that this is the plus x direction, and in principle, if there's no kink, there so the next one should be the plus y direction. But then here, if there's a kink, this will be minus y direction. So there will be a shift. And then, so how to say, after this kink, they will be still this anti-clockwise. So this minus y, and then the next one is +1. So there's a kink exist here. So you can see that. So for the other side, so the qubit is always on this x direction, plus x or minus x. And on the y, on the even side, so the qubit is on the y direction, plus y or minus 1. So we can easily find out. So the basis, so all the vectors, they are orthogonal, and they form a complete basis for the Hilbert space. So then the third one is then, so how to say, the number of kink is just the equal to the number of the system lengths. Then we will get another spin helix state, but with a different chirality. So the first is x, and then is y, is minus x plus y, with different chirality. So then we can get an solution for the eigenstate of the XY model. So we just use this, so how to say, we just use this basis to expand the eigenstate of the Hamiltonian. But here, so this is the n, it's just the number of kink. We need a sum for all the possible kink, right? And then this is the kappa is plus or minus 1, means So if this, so how to say, kappa is +1, it means in this state, in this global, in this factorized state, so the first qubit is on the +x direction. If kappa is -1, so the qubit on the first side is on the minus x direction. And then this psi can take 0 or 1. And then this, so the wave function here can be given by a very simple slight determinant. And in this determinant, so the element in this matrix just is a very, so how to say, simple function about this lambda. And this lambda and this epsilon n is just the parity of the system of the sides. And here m, the number of the base roots just has the same parity as n/2, and these base roots just satisfy this very simple Bethe ansatz equations. So this, so how to say, the states constructed in this way, they form orthogonal and a normalized eigenstate of the Hamiltonian. So then the corresponding eigenvalues of the Hamiltonian can be given by this form. So how to say, once we get the solutions for these base roots, and then we can get the spectrum of the Hamiltonian. So then is the completeness of the Bethe vector. First, we see that so the vectors in our chiral basis, they are orthogonal and complete. So then let's see the Bethe ansatz equation. This equation, we can easily prove that for if the number of base roots is m, so for each psi, we will have this n, so how to say, this is a binomial parameter, right? So select m from n independent solution for each psi. So then, because here psi can be 0 or 1, and then we will get such a, so for if the m is n, we will get such a 2 times this binomial parameter, right? It's the number of the solutions we can get in for a fixed m. So then due to this identity, we can prove that, so we can find all the eigenstates and all the spectrum of the Hamiltonian. And then is the simple proof about this normalization and orthogonality of the Bethe vector. And first we can prove that, so if they belong to different m sectors, so first the basis sector, they are orthogonal. So then, so the basis state, they should be orthogonal if the m is not equal to m prime. So for an emission system, we see that this lambda, so the complex conjugate of this lambda is lambda L is minus lambda L mod 1, and then we can prove that this so how to say, so in this factor, this complex conjugate of this factor is just 1 over this a, and then we can find a very useful identities. So a sum, we take a sum from n to from small n, from 1 to capital N. This sum is just n times the delta function. So then we, after some calculations, we can prove that, so if the base roots are not the same, and then the base states are orthogonal, and they are also normalized. So after the results, so one of our collaborators realized that, so maybe we can find another simpler parameterization than the elliptic functions. So the strategy is like that. So first we just introduce a momentum function. This e to the power of I times p is this theta 1 lambda plus 1/4 over theta 1 minus lambda minus 1/4, and just denote this pg is p over lambda g. And then we can rewrite the Bethe state just using this causal momentum. So here the state is the same. So the state is the same, but in this wave function, we also has this this determinant, but now the elements of in this matrix, in this determinant, they are all parameterized by this causal momentum P and this phi, and this phi of P depends on this Gx, Gy, and also this P. So if we, for the readers who do not know a lot about the elliptic function, we can just use this very simple parameterization directly. We just use this root of unity, and then this causal momentum. So they just satisfy this very simple basic equations. We can easily get the PG and then substitute this PG to the basic states, because we know this Gx and Gy, and then we can get this phi of P, and then we can easily construct this the eigenstates of the Hamiltonian. Okay. So then this the energy is we can also use this so how to say, we can also use this causal momentum to parameterize the energy. So if we plot these figures, so on the this is P and this is the base root, this is the momentum P, and this is the so the energy, so the E to the P, right? So we will see that there will be two branches, and there will be a gap, and this gap is 4 times Gx minus Gy. And if we let this Gxy to 1, we can get this. We can get the XX model, the eigenvector of XX model from the XY model directly. So the component with the from the algebraic beta ansatz, because for example, so we checked that so our beta states are eigenstate of the Hamiltonian, but not the eigenstate of the transfer matrix. So this make our approach different with the algebraic beta ansatz. So for a very simple example is m equal to 0 case. So in our Chiral state, so our state can be this 1 or -1, or this is a linear, or this combination of these two states. They are all eigenstates of the Hamiltonian, but for the eigenstate of the transfer matrix and also for the shift operator, we need another two terms. This is 0, this is -1. So the red one is what we select, they are orthogonal, and the blue one, they are also orthogonal, but the red one and the blue one, they are not orthogonal. So it means we can see that so in our basis we only has two terms, but for the algebraic beta ansatz, so now they have 4 terms. So more terms make it difficult to normalize the basic state. And as far as what I know, there's still a difficulty to normalize the basic state given by the algebraic beta ansatz. So then is another thing for some simple case, we checked that so our basic states are not eigenstate of the transfer matrix, but they are eigenstate of the T of U times T of V. So then the last part of about the XS model. So for the XSZ model, for the XY model, we construct some the Chiral beta ansatz, and for the X model, we can easily get the similar results. So we can get this causal momentum PG, satisfy this basic equation, and then so the wave function can be given by such a slight determinant. And for the conventional one, so when we use this all spin down and the spin flip, we can also have the same result, but the difference is what we see. So now we have 2 branches right here, but here there's only 1 branch. Another difference is here. So the number of base roots can be arbitrary integer from 0 to capital N, but here so the number of the base roots can only has the same parity as N over 2. So then is the comparison with our conventional one and the conventional eigenstate and our Chiral eigenstate. First, we for how to say, for the transversal magnetization, they are both 0. So, but for the SZ, so the conventional one, they are eigenstate of the total magnetization, but for our state not. And for our states, they are eigenstate of the winding number, but but for the conventional one, they are not the eigenstate of the winding number. So it seems, so we can see that in this state, so the total magnetization and this winding number looks like has some duality here. Another thing is that for the conventional one, so the Bethe states are also eigenstate of the one side shift operator T, and also for the two sides shift operator T square. But in our state are not the eigenstate of the one side shift. But we are also the eigenstate of the two side shift. And another difference is also about this spin current. So in generally for the Chiral states, we will have a large spin current. So then is the comparison for the Chiral eigenstates of the XS model and the XY model. So the first difference is about the energy. For XS model, this is just a cosine function, but for this XY model, we have this cosine function, but also another factor depends on this gx minus gy. Another difference is for this sigma zeta. So the expectation values of local sigma zeta. For XS model, this is always a constant. So how to say, for arbitrary n, this is same. But for XY model, so how to say, the expectation values for sigma n zeta, they are different. If the system size is order or even, they have two different values. It means for odd side they have values, and for even side they have another different values. Another one is since the vector are same, and for XS model and XY model, so for this winding operator, in XS model and XY model, they have the same value. Another interesting thing is for these two-point correlations. Although, so how to say, there's some difference between the XS model and the XY model, but for these two-point correlations, so two-point correlation function, their expectation values in XS model and XY model, they are same. So then is some remark. So for the XS model or XY model, our approach is only valid for an even n. So another thing is that we know that if we use this Jordan-Wegener transformation, and then this periodic XY or XM model can be translated to become a free-Fermion, and we can use this technique to construct the exact solutions. But now there's an open question. So what's the difference? Because what's the difference between this Jordan-Wegener technique and our approach? Because this Jordan-Wegener transformation is not local. So I don't know the answer in this stage. So this is the another thing is that our Chiral basis may work better than the conventional one to study some subject. For example, in one of our recent work, we just use our Chiral basis states to study the decay of the transversal polarization of the spin helical state in the XS model. And so how to say, we just construct such a simple factorized such a factorized state, and then to try to study the decay of these states, and by calculate the expectation values of sigma nx. And so why we do this? Because this state is factorized, and in the recent cold atom experiment, so this kind of the state can be prepared in the exponential in the cold atom exponent. So what to say? So then is the short summary. So under the root of unity conditions, we can construct and we can see the Hilbert space has an invariant subspace, and they consisting of chiral vectors with a fixed number of kinks. So then we proposed a coordinated beta ansatz to construct all the eigenstates corresponding to the Chiral invariant manifold. And for the XY and X model with an even n, we construct a complete and orthogonal set of beta states using our Chiral basis. So, and some open question is that, so in this stage, I don't know, so what's the symmetry of the system and the root of unity condition? Maybe there's some loop algebra, but I don't know. Another question is what is about the eigenstate of the XY model with generic integral boundary condition? For example, if the lattice side is not even, is odd. So then is for the XYZ model. So how to normalize the beta states? And the last one is calculate the correlation functions of the XYZ model. So that's all. Thanks.
Okay, thank you for your talk. Questions?
I really don't understand what you said, root of unity, because it is easy to see that XXZ model, if parameter anisotropy related with root of unity, it depends on what root of unity you take, because just say that alpha to the power n equal to 1, it is not defined alpha uniquely. It's up to root of unity again. And many works of XXZ model says that XXZ model depends on root of unity. What is root of unity you take? For example,
so here is
here
is for the, let's see, the XXZ chain. So for we can see that for XYZ chain we have this root of unity conditions, but for this but if we just take XXZ limit, we see that this eta, the anisotropic parameter, right? Eta here times an integer is so this is the root of unity. And for the XYZ chain, the root of unity means so for XYZ chain, the root of unity means so the crossing parameter times an integer is a combination of this tau and 1.
I want to just comment about XXZ model, because a very nice basis was construct Suzuki Takahashi, and it has a lot of application in study of XXZ model. How it related with Suzuki Takahashi basis for XXZ model?
In fact, I want to say for my understanding, for the root of unity conditions, so how to say, so for my understanding, so the basic equation should have some special solution. For example, some beta roots will go to infinity. And if you want to say, so the beta ansatz equation is complete, you should count these special solutions. But for the case, so when eta is not a root of unity, so all the base roots are finite. They will not go to infinity. That is what I want to say.
Okay, let's thank our speaker for a talk again. And thank you all for the coming. So we are finishing our seminar session for this term. So Merry Christmas, Happy New Year, or Happy Chinese New Year, because we are starting next February.